Hello everyone, my name is Yu-Heng and I'm here to present our work, BOFormer, only to solve multi-objective Bayesian optimization by Markovian IO. Bayesian optimization is widely applied to hyperparameter optimization. There are many work that focus on single-objective HPO and have a huge success. However, HPO under multi-objective setting is still an unsolved problem. So there is a direct extension of the IO method of single-objective BO to multi-objective setting. They will fail due to hypervalue identifiability issue. We propose a new AF called BOFormer, which leverages sequential modeling technique and is successful in solving an OBO. Let's start with a scheme of hyperparameter tuning of HGB boost for random boost V2. This figure presents the loop of hyperparameter tuning and the parameter including the learning rate and the L1 regularization term and the maximum depth of the tree. The performance metric we consider could be the negative loss, the area under ROC curve, and the testing accuracy. We introduce the property and the goal of the sequential optimization here. The first one is that the gradient energy is unknown and what we can do is the sampling. The second one is that the sampling under the scheme is expensive. So the goal of sequential optimization is to find a maximizer of the back-to-class function as fast as possible. Bayesian optimization is a common way to solve sequential optimization. There are two key techniques considered in Bayesian optimization. Bayesian optimization relies on Gaussian process to estimate the back-to-class function. The second one is the acquisition function, which serves as an index policy, and the posterior of the GP on each domain point is its input. Typically, most popular F are myopic. The intention of this F is to maximize the immediate improvement. Different from that, learning-based method it can achieve non-myopic F by considering the long-term reward. Besides, this F performs much differently under different type of back-to-class function, and the learning-based method can easily transfer via meta-learning. However, when we try to extend the learning-based F of single BO, they will fail due to the hypervalue identifiability issue. Let me introduce the setting of mobile here. We try to find the maximizer of the multiple objective functions. If we have many samples as shown in the right figure, we have the sample point close to the top right curve is all the best choice, called Pareto optimal. So the goal of mobile is to find all the Pareto optimal points. And there is a metric called hypervalue, which is a value of the set of points. So finding all the Pareto optimal points in mobile is equivalent to maximizing the hypervalue. So the hypervalue identifiability problem is that we find the hypervalue increment of the next sample x3 will depend on the whole history, which consists of 2 points, x1 and x2. So in this case, if x1 and x2 is here and here, the hypervalue increment of x3 will be the orange area. But if we have x1 here and x2 here, and the orange area will less than the previous one. The main idea of BOFormer is to leverage the transformer to proceed all the history information and then predict the Q value of a domain point. We apply Q-learning to learn BOFormer as the acquisition function. Here, the station period will be the posterior distribution of the Gaussian process. The reward signal will be the hypervalue increment of the chosen domain point. The empirical result consists of many combinations of the benchmark functions. And we can see that BOFormer performs well, especially in the non-smooth function, like Ackley, and restoration, and switch fault. We also evaluate BOFormer on YHPO gene. Based on this result, we have BOFormer can achieve little shot transfer to other unsafe testing functions. A quick summary is, if we want to use IO to solve an OBO, solving the hypervalue identifiability issue is a key point. And BOFormer, which leverage the transformer to solving an OBO, is the right choice.